In these sections, I'd like to explain how to solve the non-homogeneous linear systems. Non-homogeneous linear system is expressed these equations, and f is not equal to the 0. If f equals 0, it becomes a homogeneous linear system. To solve the non-homogeneous linear system, at the first step, you need to solve the associated homogeneous equations. The case of the f equals 0. Then solution is expressed x equals x sub c. In the second step, find the particular solutions. X equals x sub p. Then as a final step, build the general solutions given by sum of the two solutions. X equals x sub c plus x sub p. Now I'd like to explain how to find the particular solutions. We have two methods. First method is the undetermined coefficient method. In this method, guess the form of a particular solution from the right-hand side of the differential equations. For example, if we consider differential equation dx over dt equal matrix times x plus vector f is a 1 minus 5. If you look at the form of the f is a 1 minus 5. From these forms, we can guess the form of the particular solution should be the constant vectors. If we consider the constant vector, derivative becomes 0. Left hand side becomes 0. It becomes 0 equal 1, 2, 4, minus 1. xp plus 1 minus 5. You can substitute the expression, then derivative equals 0. So xp can be calculated minus the inverse of this matrix times 1 minus 5. Then from this equation, you can calculate the inverse. It becomes 1 over 9 minus 1 minus 2 minus 4 1 1 minus 5. It becomes 1 minus 1. This is the particular solutions. So we could find the particular solutions using the undetermined coefficient method. And second method is a variation of parameters. So again, as a first step, we need to solve the associated homogeneous equations. The equation is expressed the sum of the n terms, c sub 1 x sub 1 plus c sub 2 x sub 2 plus blah 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 up to the c sub n x sub n. So if you use a component, this is the expressions. Then we could combine these n terms into the product of the matrix and the vector quantity of the c sub 1, c sub 2 up to the c sub n. Then this matrix is we name it the capital phi as a function of t times the vector quantity of the c. So we call it this is a fundamental matrix, mental matrix of the systems. Then by combining the original equations, the phi prime equal a phi. So we find the equation for the phi's. In the second step, we find a particular solution using the variation parameters. If we consider the constant c, it's the solutions of the homogeneous equations. So instead of c, we consider the u. U is a function of t's. Then substitute into the non-homogeneous differential equation, this differential equation. Left hand side is a x sub p primes. You can substitute this expression here to find the derivatives. Product rule for the derivatives. So phi prime u plus phi plus u primes equal substitute this x into the here. So a phi u plus f. Then we have find that the phi prime equal a phi. So we have these equations. Then this phi primes a phi is exactly equal. So these two terms is cancel out. So equation becomes phi u prime equal f. Then you can multiply the inverse of the phi in the both sides of the equation and integrate to find the expression of the u's. So general solution is a sum of the complementary functions and the particular solutions. First term is a complementary functions, and the second term is a particular solutions. So using the variation parameters, we could find the particular solutions. So this is an example. Use the variation parameters and find the solution of the following non-homogeneous systems. As a first step, we need to find out the solutions of the associated homogeneous equations. So we have discovered these solutions. Xc is expressed c sub 1 1 exponential 3t plus c sub 2 1 minus 2 exponential minus 3t. We derived these solutions when the characteristic equations has two distinct eigenvalues, lambda equals 3 and minus 3's. So from these equations, you can build a product of the matrix and the vector of the C. And this phi, we find a form of the fundamental matrix. Once we find a fundamental matrix, we could calculate particular solutions by substituting the fundamental matrix here, and we could calculate the inverse of the fundamental matrix. And this is F, form of the F. Then we could perform these calculations. This becomes exponential minus 3t minus 2 exponential 3t dt. So it becomes 1 over 3 exponential minus 3t 2 exponential 3t. Then multiply fundamental matrix with this 2 becomes 1 and minus 1. So this is a particular solution. So general solution is given by the complementary solution of the xc and the particular solutions. Okay, so I explained the two methods to find the particular solutions. First method is the undetermined coefficient method, and the second method is a variation parameters. So I explained how to solve the system of differential equations in these chapters. Okay, this is end of this chapter.